So far we have only constrained ourselves to talk about breakdown under uniform fields. But what happens when a gaseous medium is present and on it a non-uniform field is uh, impressed? When you have an non-uniform electric field, the situation is quite different from uniform fields, and therefore the breakdown in a non-uniform field is hardly likely to be either due to processes similar to a Townsend mechanism or the Strimmer mechanism. Something very different is likely to happen. Now, when I talk about a non-uniform field, we can talk about various kinds of non-uniform fields. Some fields are more non-uniform than others, and we have discussed earlier, we have seen earlier how different kinds of electrode systems can give rise to different kinds of non-uniform fields. I consider here the needle plate gap, which is the most non-uniform situation that you can imagine. This is, let's say, the needle. This is again a finite element simulation of the non-uniform fields that would happen when you have a high voltage electrode which is needle shaped and you have the ground electrode which is a plane. As you can see, the field is very low between these lowest values possible. In most of the regions, if this entire region is covered with gas, is filled up with gas, and in most of the region, the field is quite low. However, as we come to this region, the field keeps increasing. So first you have dark blue, and then you have cyan, and the field is quite high in the region where you see the contour map to be yellow. And then in this very small region, which is red, the field is maximum. Now these values 1000, 2000, these are not, these are just take them qualitatively. Do not take them quantitatively. What I'm trying to say is that the field is graded in such a way that you have pretty low fields almost everywhere within the gaseous medium, but in a very small region the field is high and the field is maximum at the needle tip. Now imagine that this is air, and we already know that the breakdown strength of air is something like 30 kV per centimeter. So let us imagine that this blue region corresponds to something like 10 kV per centimeter, which is considerably lower than the breakdown strength of air. So when you impress this field on the gas or air, the air is not going to break down and you are okay. But even when the field is something like 10 kV or 15 kV in this region, the field will be considerably higher, and it may so happen that just in this small region, which is colored red, the field is higher than the dielectric breakdown strength of air. I'm taking air as an example. So let's say everywhere it is 10 or 15 kV centimeter, 10 or 15 kV per centimeter, whereas just in this red region, it is, let's say, 45 kV per centimeter. And that is way above the breakdown strength of air. So what will happen in this situation? In this situation, you are not going to have breakdown of air, in the sense you will not have a conducting path created from the high voltage electrode to the low voltage electrode, because let's say in this cyan region where the field is higher than elsewhere, even then let's say the field is like 20 kV per centimeter. But in this red region where the field is considerably higher than the breakdown strength of air, the air in that small region is going to be ionized because there is a localized field enhancement, and in this region of localized field enhancement there will be ionization of the gas or air. So what happens is the gas only confined to this red region is going to break down in the sense there will be ionization. As a result, there will be charged particles, and these charged particles will move around in this region, which means there will be current, and whenever there is current, there is heat loss. So this process is called partial discharge or corona. So what is partial discharge? A partial discharge happens only in a non-uniform field. It is not a breakdown in the usual sense that there is no conducting channel formed bridging the two electrodes, the high voltage and the ground, but there is only a partial breakdown of the insulating gas in the region of localized high electric stress. So in a very small region, there is a high electric stress, and only within that region, the gas will break down partially. This is called partial discharge, or PD. We will study at considerable length about PD later. Right now, uh, the only point that I want to make is that PD is important to us because when PD occurs, you do not have a channel bridging the two electrodes. So even when you have PD, the insulating material, the dielectric material will continue to behave as a dielectric and will provide insulation. The problem is that there will be some losses, but it will continue to provide insulation and you don't have failure. However, over a long period of time, if PD continues to happen, then there will be degradation and there will be other processes which we will learn later, by which a conducting channel may be created between bridging the two electrodes. And at that point, failure, dielectric breakdown, failure or puncture will happen. So PD in itself is not that much of a problem in the sense that the dielectric still continues to retain its dielectric property, if not wholly. However, PD can ultimately, over a long period of time, lead to catastrophic failure of your gaseous or other solid insulating material, which we will see later how that can happen. So this is PD and it is important. Now, what about corona? What is corona? Corona is nothing. Many of you might have heard about corona because corona is those kinds of PD which are visible. When partial discharge happens in air, it is called corona. So partial discharge can happen inside an solid. Let's say inside a solid material you have a void encapsulated, and within that void you have air, and only a part of that air or that entire air void breaks down. So there is a partial bridging of the insulating material, bridging of only the gaseous portion, but the remaining solid portion remains unharmed. This kind of PD, which happens inside a solid material, is termed as PD. Corona is the same thing happening in a gaseous medium, where a part of the gaseous medium becomes ionized and breaks down, but there is no full conducting path between two electrodes. So corona is nothing but PD in air. Why is corona called corona? Actually, the thing is that well before people came to know about, could register the existence of PD, people were aware of corona happening. The word corona comes from the Greek word which means crown. So in earlier times, sailors used to sail the seas, and in the ships there were very high masts. And on a foggy day, what they would see is, they would see that the tip of the mast would glow as if it was on fire. And they called that Saint Elmo's fire. So they always related everything to divinity. They called it Saint Elmo's fire. And because it looked like a crown on top of the mast, it was called corona. And nowadays, we are familiar with corona because corona is one of the problems that we have to consider. One of the problems that we have to consider in our design of transmission lines. Corona happens in transmission lines. Many of you, if you have been traveling, let's say the countryside where you have these huge transmission towers and the high voltage lines, and on a rainy or a foggy day, you might see a white glow along the transmission line. And that is corona. So let us first learn more about corona, and we'll learn about PD later.